All right, everybody. I'm going to talk about the Gaussian Splats pipeline in Houdini today. But first, let me introduce myself. My name is Sanitra. I'm a Houdini generalist with passion for FX, and I currently work at Nvidia. And maybe some of you can remember me from last year's presentation about the NPM solver and the cream and cookies demos. But today we're talking about the Gaussian Splats, of course, about the pipeline SideFX built for us to generate those, and I'm going to demonstrate the work in the pipeline with some of the examples of our typical assets like volumes or animated G-splats. We're going to capture some of the characters and intricate details in fur and look at the environments capture or interior exteriors. And I'm going to wrap it with some current issues or limitations or where this really shines, where the G-splats are really doing great. So we're going to have a look at this explosion. This is actual G-splat rendering in the viewport. So are these clouds. And we're going to animate this palm and convert it to G-splats and capture these characters, intricate details in fur. You can see the G-splats capturing reflections in the eyes, and we're going to have a look at this bar scene from the content library and challenges there with capturing interiors. All right, so for those of you who have no experience with Gaussian Splats, what are those? Of course, we are Houdini artists, so for us it's just points with attributes. But better definition will be of Gaussian splat is an anisotropic ellipsoid with multiple attributes. And same primitive can be a sphere, like you can see there on the left side, or a flat disk, or a hair-thin strand. The important thing is that each of these points carry this spherical harmonic function, and that describes how the splat behaves from different viewing angles. So the result is really view-dependent. And then, of course, the job of the pipeline we have in Houdini is to figure out how to rearrange these points in 3D space, how to scale them, orient them, what attributes or color information or AOVs they carry, how opaque or transparent they are, and then we can stack them together and reassemble the final image with them. And then, of course, when we have those splats, we need to render them. And that's actually the easy part. We just sort them front to back and stack the alpha of those splats. Similar what you can see on those squares there. Imagine those are your splats. And in cameras that they have different opacities, and you stack them, and then you're moving sideways, and the parallax will create this illusion, for example, of the reflection in the eye or specular highlights. And here you can see, for example, on these whiskers, the individual points, those are those G-splats, but they are so stretched that they can form these whiskers from very few points. And here you can see how you can capture the intricate details of the fur with this simple method of stacking opacities and stretching disc shapes. All right, so let's see how we can do this. SideFX prepared this recipe for us. You can just drop it right away in the Solaris in the stage on the Solaris content, and basically you are ready to go with a single click of a button. And all you need to do is load your asset in a sublayer or reference or SOP import, and then execute the graph. And under the hood, there are a couple of things going on, and we will look at all the individual pieces of that process, which will be generating camera rig, then generating the ground truth renders, initial point clouds, training, and exporting to final assets. All right, so first thing, of course, to do is we need to create these cameras, the viewpoints that will generate the ground truth images that will go into the training. And for that, of course, Houdini, this recipe will do it for us. And as Jacob was showing already, there are plenty of options, controls for you to cover your subject perfectly. And you can also feed your own cameras, because now in Houdini 22 we have cameras in SOPs, so you can just copy 2 points, any cameras, you can create rigs like this with copy to points in seconds. So it's super easy to work with the cameras. Of course, for the interiors and exteriors, the coverage of the subject is a key factor, so you need to work it a little bit more, but I'm going to show that in the later sections. And here is such a camera rig that looks almost like Paul Debevec light stage, right? Trying to capture this hamster model. So these are all the cameras I used to render the ground truth images. Right, so when we have our camera rig set up, we need to of course render those images, generate the training data for the training process, and you can render those images with anything you're really using in Hydra. If you're using Karma, Redshift, Arnold, RenderMan, anything will work. The important bit is that you need to render the OpenXR format, because the camera metadata is embedded directly into the file, so you don't have to provide the camera as a separate assets. And also the OpenXR will store the depth information, so you can easily generate the initial point cloud from that depth and transfer or project back those OpenXRs to the points, including every AOV or any other data you have. And then you end up with feature carrying point cloud that basically holds the information, all the information you need to get that training going. And here are just some examples of those ground truth images from those cameras I rendered in Karma XPU for the training of the cloud asset. And as Jakob was mentioning before, the good news in Houdini 22 is that we don't only train the basic RGB information, how we actually see the G-splat, but we can also train any extra features coming from AOV layers in the OpenXR. So if you have, for example, normal map or albedo or subsurface for the leaves, for example, in the scene, then you can train that as well, and basically you will end up with a G-splat of normal map. So this is a actual G-splat displayed in the Houdini viewport of a normal map of this palm. And why that is important? Because then you can really use a G-splat as a format or a container that carries all that information, and in COPS with the new nodes you can rasterize those two planes and work like if you were working in Nuke, when you can relight it, change the compositing, change the look or layers and contributions. So you have really a proper compositing with G-splats, same way as you have with OpenXRs. And as far as the actual training process goes, that is running in a TOPS graph. And in each step, the algorithm is comparing your current version of your splat against the ground truth images. And it's pushing those points towards the better fit. So it's trying to find positions, orientation, scales, and training the data of those individual points to really represent your asset as best way possible. And there are two ways to do that. One is called default, and the other one is Monte Carlo. And the main difference is between them that the default algorithm is adding and removing points. So your point count is changing during the training process. And in Monte Carlo, you can set a fixed limit. For example, you just want to have 100,000 points in your G-splats, and then the algorithm will just move those points around and retrain them. So your point count is fixed. And we have three schedulers here. You can see on the bottom of the graphs. And those are important for us because we want to have as efficient as we can usage of our hardware. So we, for example, need to render those ground truth images. We want to set that, for example, to submit on a farm or to render 5 frames at the same time on our hardware. And then for the training, we want to submit it, for example, to the GPU number 3, because that's the one that has the most VRAM. So that's how we can configure the efficiency of the execution of this training graph. And of course, when the training is running, this is something you will see the so-called triptych, or you get these three images when you have the ground truth on the left, then your current version of the G-splat in the middle, and then the noise or the heat map, very similar to what you are used to from rendering. When you are inspecting the noise or the problematic areas, you will see the same here. The red areas are showing the areas where your G-splat is not yet matching the ground truth, and the blue areas are very close to the ground truth. And of course, that's interactive when you training. So here's how the blue is changing, the hues are changing, and how the center image is becoming more and more like the ground truth image on the left. And here's the live training monitor tab, which is the new tab SideFX added for us to actually see the actual values of noise loss and number of iterations, and these more technically important data. So here's one of a graph that explains really well the strategy, the training, and the process of the training. So this is for training the furry character, the hamster model, and on the x-axis you will see the number of iterations. I've trained this 400,000 iterations, and on the y-axis we can see the number of points in the final G-splat. So we start with seeding 1 million points, and then we start the training process, and right away we drop to around 200,000 points. And then this is the default strategy, which is pruning and growing. So it's adding and removing, adding and removing, adding and removing. That's why we see this so shape growing and removing. And after roughly 20-30,000 iterations, the algorithm will realize we have enough points to describe our scene, to our model, our asset in a way that really matches the asset. So then it starts to remove more, just adding a little bit, remove more, and then you see the number of points in the G-splat is dropping, and around maybe 400,000, 300,000, you start to kind of flatten out, plateau out, and then that's the territory where you basically are starting, or you are in diminishing return territory, where you are training, but you are not getting much of a better result. And you basically training noise, and you should probably stop the training. You can observe very similar behavior here on the, if you're watching, for example, the noise loss, the drop is almost linear till like 30-40,000. That's where the core of the work is getting done, and then after 50,000, basically flat. So if you training and you observe this graph, you will see that you're basically wasting resources. I trained it 400,000 when, for example, 10 minutes, when I could have already been done by 5 minutes, yet 50,000 iterations. And of course, you can specify the target point count of the G-splat, so you can really go with high fidelity or light wave G-splats. And here I've prepared a bit of a comparison for this hamster. When we will see the actual G-splat rendered in the viewport, and the point count or the points representing those G-splats. And this is with 300,000 points, and I will go down to 80,000 and 20,000 and down to 5,000, and you will see how that translates to the quality of the G-splat. So we can see that dropping down from 300,000 down to 20,000, which is a magnitude difference, it's definitely not 10 times less representation of that same subject. So G-splats really holds really well at low splat counts. And here's the same for the face. And if you look at the mouth or nose area, you can see those small, like individual, almost like a brush strokes like shapes, and those are those G-splats that are oriented in certain way. So we are looking at them right now, we see them as the strokes, but from the side, for example, they actually represent that surface. And of course, like during the training, you're getting some checkpoints, so you can, in case you crash or abort, you don't lose your work. So every 10,000 frames, you can export, for example, the PLY file, which is the native format for G-splats, or you can also export the USD file. And also you can partially restart or retrain just some specific data, like, for example, you already trained your G-splat with just RGB, and you want to add normals to it or subsurface, then you just restart from your existing model and only train that new coefficients. All right, so we're going to have a look at some more examples and start with volumes. So, of course, volumes, they have no surface. And they are just a continuous distribution of density, and density stacking is what makes volume works. By that I mean you have voxels, they have some density, and you have many of them in camera Z depth, and you're stacking them together. That's creating the illusion of the representation of the volume of the cloud or the explosion. And something very similar is happening with G-splats. You have these ellipsoids that are stacked in the depth, and they have opacity instead of density, but the mechanics is the same. You're stacking multiple elements together and creating the image. Therefore, the volumes are really great candidates for G-splat representation. And of course, the optimizer, there is no surface on the volume, so how he decides where to put those individual splats? Well, they will be put in the areas of the most variation or more visual interest in the image. So in the explosion, where you have a lot of contrast, a lot of changes in the data, there will be a lot of points. Same for the clouds. You will have a lot of G-splats on the edges, but very little. For example, in the center area that is very flat, there will be very few G-splats in there. And so here's our explosion. This is actual G-splat rendering in Karma viewport. And why I'm showing is because I want to point out one very important information, and that's that G-splats actually can carry high dynamic range data. So if you rendered your ground truth images of this explosion correctly to OpenXR without clamping, that will translate into the G-splat. So if we have a look at our G-splat, the values, for example, are over 30 here in this G-splat, which means that if you put it in your environment, you can basically illuminate the environment with the G-splat. And also worth notice is the file size reduction. Of course, the original VDB was 1 GB, and G-splat will be 10 times less. So they are really useful representations for volumes. So here's the actual explosion and the G-splats, the points representing the explosion. All right, so let's have a look at clouds, my favorite. Clouds, of course, are very interesting because they have this anisotropic scattering, right? Because it's mostly water, very strong forward scattering. So when you look at the image on the left, you will see we are looking along the light direction, and that cloud looks pretty flat. And compared to against the light, you will see all these nice highlight edges and light scattering through. So you will see those white boiling shapes. That's the anisotropic scattering through the cloud. And of course, G-splat, being anisotropic and being viewport dependent really captures this phenomenon really well. And of course, clouds are notoriously slow to render because they take many bounces in array. So sometimes you're rendering clouds for hours if you're doing fly-throughs. Compared to that G-splat, you have this G-splat will render it like 100 frames per second in the viewport. And the match is almost like 1-to-1 with the offline render. So here's that cloud. And here we can see the anisotropy, like from this angle, looks very flat. And as soon as we start to rotate, we'll see a bit of almost like a specular highlight on the edges. And then you'll see the rim light and the scattering through the cloud. So from this angle, really it looks different than from the other angle. And here's the what I was talking about, the position of those G-splats on the cloud. You can see the clustering, that fractal, cauliflower shapes. You can see the points being mostly on the edges, on the area of visual interest, and there in the center there are almost no points, almost no G-splats, because in render there was a bit of a shadow, so those shadow areas can be represented with much bigger or smoother splats. And the edges, they really need to stay sharp, so you have a lot of points there on the edges. All right, so let's have a look at how we can animate G-splats. So I will show it on the example of this palm, which of course I had to only train this G-splat once on a static pose, and G-splats, of course, they are just, for us Houdini artists, just a bunch of points with attributes, so we can manipulate them as we see fit. So we can use any existing tools to deform it, so in my case point deform, or you can use lattice wires. For characters, you can rig. You can use the same rig to rig your G-splat and have an animated character as a G-splat. So there is no preference training needed most of the time. You're just driving that single G-splat with the Houdini tools as you usually do. So here's that palm, which I think was maybe 50 or 70,000 points. The original was a million polygons maybe. So super lightweight, holds up pretty well from those couple of points. And of course, when we have animation, we usually need to store it in some way. And for that, USD is a great candidate, because Pixar in this year release added a new USD schema for Gaussian Splats. So the Gaussian Splats are now first-class citizen in the USD world, and of course Solaris, reading all the USDs natively, can read them as well. And that way you can really store efficiently your G-splats on disk, because you will only time sample really the changing properties or primvars. So if our palm G-splat has opacities, orientation, positions, and spherical harmonic functions, you only time sampling position as the points are moving, you time sampling orientation, and everything remains is just static properties. Animating a G-splat of a palm like this will be maybe in hundreds of megabytes, compared to the polygon model. It will be in gigabytes of caches for that mesh for 600 frames animation I was doing. So here's just the palm in a viewport natively as a USD primitive, and here's the wipe of showing the point counts on the palm. And this was trained with subsurface and normals and albedo and all that, so you can see like the leaves have nice subsurface there on the top, and as we start to rotate, you will see some specular, and we start to rotate more at different angle, it will become flat again, because the light is not hitting it, so it's really nice and interactive, and the anisotropy is there captured in the G-splats. Alright, so let's have a look a bit at the characters. First, I want to thank Lorraine Evers for providing these beautiful models. I had so much fun trying to capture these. And of course, characters, they have very intricate surface detail. They have fur, hair, whiskers, and translucent tissues like these ears. So usually it's quite challenging for path tracers, as we all know, rendering very, very thin hair, sub-pixel size. So I really wanted to see how G-Splats can deal with that, and I was really surprised that G-Splats are such a good fit for capturing fur, especially for this cat. I really wanted to push it, so I've rendered like 2K renders, maybe 300 cameras or something, and tweaked the optimizer, and I think it's representing that subject really well. Everything to single one, every single hair is there in the model. And here's our furry hamster with all those details as well, those individual hair strands. And here I want to show the anisotropy as well. The fur from this angle is pretty flat. And as we start to rotate, you will see the hair will get nice backlight and transparency showing. And again, as we rotate, it will be rather flat. And also the specular in the eye is moving. It's very interesting because there is no surface, right? Just those ellipsoids stacking and creating the illusion of moving specular. And here's the cat. I want to see showing the points here. I think it was nearly 500,000 or something points for this cat. But the match to the offline render is almost like 1-to-1 quality for the offline render. And the speculars in the eyes are moving. Again, it's very similar to the hamster. All right, so what about the environments? The last bit we did not cover it. So let's have a look at this bar scene. Of course, the bar scene, I name it as an honest case, because this bar is a kind of subject where this really gets harder, but not because of the pipeline, but because of the inputs. Like the bottleneck, of course, is the data set you are feeding to the training, the ground truth images. And your splat is only ever going to be as good as your input. So the environments really are the category where the camera coverage gets tricky because you have a lot of surfaces, and sometimes you are seeing them from very awkward angles, or you don't see them at all. For example, under the table, like behind the bottles, behind the bar, or under the counter. Or really, if you don't place a camera there, you will not see that. You won't be able to generate a G-splat from something you never saw. So no matter how many cameras you have or how hard you train, if you don't have the coverage, you will not be able to generate the G-splat. And of course, after I realized that designing the camera rig actually was the task I need to overcome. And I found this paper from 2024 on the optimal camera placement. So I just implemented in Houdini Wrangle, and you just pipe the geometry into the wrangle. It will mathematically position those cameras based on how much they overlap, if they are seeing the same subject from multiple angles, if they are occluded, and so on. So if you ever going to capture environments or interiors, you really need to treat this camera placement as an engineering problem. That's the right mindset. You will not succeed with spherical rig around the scene, right? And here's how the bug looks captured. And now I will show this interesting bit from the outside that probably nobody ever saw. Of course, there's nothing outside. And that will bring me to some of the issues and limitations, or how they can manifest. So I freeze this frame from the outside. You will see a very interesting shapes in there, like big soft blobs, or these long spiky regions, or wrong colors, suddenly some green colors there, right? But this is all the same dominant failure mode. Simply, we don't have cameras there. We haven't not seen that subject, right? Or we see it from very few angles, so we cannot really model or represent those areas without knowing anything right about it. So that's the major failure if you start to see stuff like this happening in your viewport, that's a coverage problem. Of course, glass refraction mirrors, basically they change look based on your camera, so each ground truth image will give you different information, so you just can't model that correctly. All right, so what about the other things to watch out for? Of course, the HDR clamping I mentioned. If you clamp your images, of course, you will get very flat and boring looking G-splat, so don't clamp your images if you want to have nice and rich interior scene with a lot of lights and interaction. Of course, when you are going to train, you need to generate those ground truth images. So that's a compute heavy operation. Like if you want to have 500 cameras for perfectly cover the bar, you need to do 500 renders, right? So you need to really plan a little bit for it. And of course, when you're going to train the G-splat, the more images you have, the more resolution they have, the more VRAM they will consume during the training process. But but I think it's not so critical. For all these assets, I trained under 16 gigabytes of VRAM, so even on consumer grade GPUs, you can create nice G-splats like this. Of course, another kind of drawback here is the temporal solution for G-splats, because there is no native as in algorithm or in code way how to train animated G-splats. So sadly, at this point, the animation is what I was showing: capture single G-splat, deform it, or very costly per frame training. And of course, at this stage, there is not many tooling for manipulating G-splats. Like you have Photoshop for images, it would be nice to have something like that for G-splats. But on more positive notes, let's see where this really wins. As I was saying, volumetric capture, smoke clouds, and stuff like that. That's a natural fit, right? We can capture those super easily. They render at the real-time speed, giving us really the offline quality. So that's really great case for using G-splats. If you are using or producing on virtual sets, or doing set extensions, or using backgrounds, virtual backgrounds, you can use G-splat because they have, of course, high dynamic range, so they will respond very nicely to your camera. And there are definitely cases for real-time previous application, because G-splats are super lightweight, right? A couple of megabytes, a couple of thousand points usually, and again, they render the real-time speed. So you can really configure your training for a specific budget you need, and you can use it for your real-time stuff. Or you can use it in the pipelines, for example, as a USD display purpose, because they are native now on USD, and if you're using asset and you need a better viewport representation that is still very lightweight, you can use, for example, G-splat for that instead of some couple of polygons, models. And of course, the biggest win here is for Houdini, because this pipeline is really end-to-end, and with a single graph, single execution, you get the final product as USD or as a PLY directly, and you can make that, for example, dependent on your asset publishing. So if your modeler publish new asset, you can kick off this task of generating G-splat automatically and use that directly as a USD preview purpose, for example. So it's really end-to-end automated. You can distribute it on a farm and batch process it and so on. So I think it's the first end-to-end pipeline that some software have. So the Houdini, I guess, it's the first here. All right, and I guess that's it from me. All right.
Super cool. We're pretty short on time, but I think maybe one question here.
Hello. Thanks for that great presentation. I was just interested about lighting them in Karma, because I think you mentioned maybe you could light them in COPS or relight them in COPS, but in the previous, in 21, I don't think I could really do much lighting with them in Karma.
Yes, there are new nodes in COPS that are aware of the G-Splat format, so you can just do sub import and it will recognize it's a G-Splat. And then you have new nodes for that's called, for example, G-Splat rasterize, that you can pick any like a layer basically from the G-Splat, so you can rasterize RGB of the G-Splat, rasterize albedo of the G-Splat or normal of the G-Splat, and then basically you have those as image planes, and you can do your standard compositing stuff. So for example, you can have like a row lighting path, right, and you do add your lighting and with COP nodes, and then you can add subsurface on top of it, for example, or adjust colors, mask, whatever you want, and then you rasterize it from camera. You can also bring to COPS. So basically, you have like a 3D composition options. You can modify those, relight those in COPS. And I think there were some videos already on the YouTube. Some other guys showing how you can relight those in Houdini.
But sorry, in Karma, so in the Solaris bit, can you put these G-Splats in and then relight them there? Because currently I couldn't do that in 21, I don't think. With that.
Yeah, you can just load it like a usual primitive, like any other geometry in Solaris, and you can put lights in there and everything. Yeah.
Okay, brilliant. Great.
Yeah, really cool stuff, Peter. Thanks for taking us through that.
Right.